Hello everyone, welcome back to my YouTube channel Unfog with Dr. Athar Parveen. This is the third lecture of chapter Optics based on HSTR and KREIS syllabus. In the previous two lectures, I have finished this syllabus which I have underlined with red lines. In this lecture, I am going to complete this part of the portion, which is the dispersion of light through prism, dispersion of light, scattering of light, total internal reflection, optical fibers and their uses, optical instruments, that is simple and compound microscope, telescope and their magnifying powers. And the rest part, that is the theories of light and polarization, that I am going to cover in the next lecture. Okay, so let's quickly start this lecture. Before starting the lecture, I would like to request you all to subscribe to my channel, and also if you like my work, please do like and share my videos. Okay, see, don't feel that still HSTR notification has not come and don't stop your preparation. I would suggest you all, it's my humble request, please don't stop your preparation, because you never know, HSTR notification may come anytime soon. In fact, now it has been told that they have divided this HSTR and PU college teachers, means HSTR and PU college recruitment. That will also come, it seems, very soon. So I will try to take classes for PU college recruitment also, especially physics. Okay. So I request you all, please don't stop your preparation. Do watch my lectures and keep your preparation on. Okay. Till now in our optic lectures, the two lectures which we have done already, we have spoken about reflection and refraction. In this lecture, we will talk about dispersion and all other topics, that is the optical instruments. And also I am going to discuss around 25 multiple choice questions. These are all the expected questions which can be asked in HSTR and KREIS. So please stay tuned and watch the lecture completely. Now, what is dispersion? Dispersion means it is nothing but separation of light into colors, and these colors, they are arranged according to frequency. We have discussed all about dispersion in our GPSTR classes also. But there, no, we did not go into much deeper. Now we will have to go into much deeper, because this is HSTR, right? GPSTR was a very easy exam when compared to HSTR. So, if you take a prism, dispersion by a prism, it makes the components of the white light visible. Those white light components, they are splitted. Once that white light is incident on the prism, and when it comes out of the prism, you can see all the colors which are present in the white light. All the colors means the wavelengths, the intensity of light as it varies with wavelength or frequency. This together we call it as a spectrum. Okay, see, from red to blue, the Vibgauer thing. Violet, indigo, blue, green, yellow, orange, red. This is how the wavelength increases. The wavelength increases from violet to red, isn't it? Now this violet, it will be most bended, and red, it will be the least bended thing. These wavelengths are very, very important, because this is how the order of the dispersion is happening in the spectrum. And we know that frequency is inversely proportional to the wavelength, right? So we can also say that the separation of light into colors is arranged according to frequency. In place of wavelength, you can also put frequency, but then just remember that frequency is inversely proportional. When you say that wavelength is increasing from violet to red or blue to red, you will have to say that the frequency is decreasing from violet to red or blue to red. Okay. Now, formation of rainbow, it is one of the main application of dispersion. Here, what is a prism? Prism will be the droplet of water. How is rainbow produced? It is produced after the rain. What is happening? By reflection, refraction and light dispersion, this rainbow happens. Here, the water droplets play the role of the prism. The light, when it was falling on the prism, it was getting splitted, right? Now the light, when falls on the water droplet, it will get splitted, and you can see the rainbow in the sky. We know that the violet is the most deviated and red is the least deviated color. This you can see in the rainbow also. Here is the depiction of how the rainbow is formed. You can see that when the sunlight is falling upon the water droplet, then the violet is the color which is most deviated and the red is the least deviated color. In middle, the all other colors are there. The Vibgauer colors are there. So this is how rainbow is formed. Now there is one necessary condition for the formation of rainbow. Simply rainbow doesn't form. It doesn't form whenever it rains, it doesn't form, right? Rainbow doesn't form whenever it rains. It will form only in the presence of raindrops, but the sun should be at your back. Then only you can observe the rainbow. Obviously, isn't it? The light is falling on the raindrop and you can see the dispersion of light in the form of rainbow. But then that sun should be on your back. Then only you can observe the rainbow. This is the necessary condition. This can be asked as a MCQ also. So you should know it. Now for the similar reasons, the sky is also blue, right? We can say that the sunlight, it reaches the Earth's atmosphere and this light, it is scattered in all directions by the gases and dust particles which are present in the atmosphere. Because we know that the violet color is scattered more, but then we talk about blue more. The blue color is scattered more. That's why we can see that the sky is blue. So if there is a question, why is the sky blue? You have 4 options. In that, scattering should be there. That is the right option. Okay. See, for example, if you have a question like this. When light enters the atmosphere, it strikes on extremely fine particle which deflects the rays of light in all possible direction. This is due to, yes, it is scattering of light. The color which is scattered most in atmosphere is, yes, it should be blue. If in the option violet was there, you would have ticked violet. But usually they don't consider violet. Everyone considers blue as the color with the least wavelength or a highest frequency. Okay. Next question. The phenomenon of scattering of light by the colloidal particles is known as, yes, it is known as Tyndall effect. See, we are talking about the colloidal particles. There are certain type of particles where scattering of light is happening by these colloidal particles. That type of scattering is known as Tyndall effect. This is a particular name given to the scattering when it is happening by colloidal particles. Next question. Which of the following color is visible spectrum has longest wavelength? Of course, it is red. Least is the violet. Highest is the red. If it was frequency, then we would have told violet. Okay. Because frequency is inversely proportional to wavelength. Now let's come back again to refraction and dispersion. But this time we are talking about a prism. Refraction and dispersion of light through a prism. As I already told you, dispersion of light through prism means, see, it is a phenomenon of splitting of white light into its constituent colors. Its constituent colors are Vibgauer. But then when we are talking about the prism, we should know the refractive index of the material with which that prism is made. That particular prism is made with one particular material, right? So we should know the refractive index of that material. How you will know? This is the formula for that. Refractive index is equal to sine of A plus delta M upon 2 by sine of A by 2. Now if we talk about the scattering of light, as I already told you, when a ray of light is incident on an extremely small object, the object deflects the light in different directions. Means that's why that word scattering is there, right? Now keeping these two things in our mind, we should know that the intensity of scattered light is given by Rayleigh's law of scattering. This scattering was explained by Rayleigh. He is a scientist who gave this law, which was named after his name, Rayleigh's law. He told that the intensity of the scattered light is inversely proportional to 4th power of the wavelength of that light. If you remove the proportionality symbol, then you add one constant, right? That is K. That is the constant of proportionality. So this intensity is inversely proportional to lambda to the power 4. This can be asked as MCQ. You should know it. Also, Cauchy gave one dispersion formula which was related to refractive index. Here mu is refractive index, okay? This refractive index is equal to A plus B by lambda square plus C by lambda to the power 4. Lambda is the wavelength of the light. A, B, C, these are the constants which are different for different material of the prism. Okay. For one particular material of the prism, that constants will be same. It is like that. Okay. So this is Cauchy's dispersion formula. Now this refraction, it also leads to optical illusions. We know, see for example, if you see, if there is a coin in that cup and if you fill water with it, with one particular angle only you can see that coin. Another example is when there is a fish in the water, you see that fish's position differently. Actual position is different. Okay. So this is also happening because of refraction. This is an optical illusion. In our science exhibitions in our schools, we used to do these experiments, right? We used to put coins, we used to put one pencil in the beaker filled with water. Then we would say that the pencil was not forming one straight line. It was bending, right? So that is all because of refraction. Now there is another very important phenomenon known as total internal reflection. What is this total internal reflection means? See, as the name indicates, if there is total reflection of the light, then you call it as a total internal reflection. Why you call it as an internal reflection? Because that reflection is happening inside the medium. That's why you call it as total internal reflection. If there is an angle of incidence beyond which rays of light passing through denser medium to the surface of less denser medium, they are no longer reflected, but they will get totally reflected. Here you can see the figure. In this figure, if a torch is put in the water, the rays, it move outside. If they are moving outside the water, means denser medium to less denser medium, or you can say denser medium to rarer medium, you say. Air is rarer medium, water is denser medium. But if you change the angle of the torch, there comes one point where that light, it will get reflected back into water only. So that angle before which the water is getting reflected into the water only. So the angle of the incidence before this total internal reflection happening is known as critical angle. It is the minimum angle of incidence inside that medium at which light ray will be totally reflected inside that medium only. Light emitted in water, it is partly refracted and partly reflected at the surface. But beyond this critical angle, this beam, it will get totally internally reflected. This is known as total internal reflection. Now we shall talk about this critical angle. If you want to find the critical angle, the formula is sin I is equal to 1 upon mu. This mu is the refractive index. I have written here R and D because it is that refractive index is of the rarer medium with respect to the denser medium. Or if you put it in the vacuum, say, if the rarer medium is air or vacuum, you say, then you just simply say that sin I is equal to 1 upon refractive index of that medium. IC is the critical angle. Okay. Now there are two important conditions for total internal reflection. First is that the light must travel from optically denser medium to rarer medium. Either you say denser medium to less dense medium, or you say denser medium to rarer medium. That is, object is in denser medium. Remember. Next point is that the angle of incidence should be greater than critical angle for the given pair of media. If the angle of incidence is less than critical angle, then you will never get total internal reflection. Obviously, right? Your angle of incidence should be greater than the critical angle which is going to occur after some reflections. Then only you will get one total internal reflection when you are getting the critical angle. Now, two more important points which we need to know about the total internal reflection are that this in total internal reflection, there is practically no loss of light. This is the one very good speciality of total internal reflection. There is no loss of light. And the second is that all laws of reflection, they hold good for total internal reflection also. So we don't need to read again any other laws of reflection. So we don't need to read any other optical laws which are dependent on a total internal reflection, because all laws of reflection, they hold good for total internal reflection. Now one important phenomena which is based on total internal reflection is the mirage. Here I have shown you the figure how you see this mirage. Mirage means in the desert area or even in the road while we are going, when it is very hot day, you see some optical illusions. You see that on the road there is some water From far you are seeing, you are finding some water on the road, but when you go nearby, there is no water. The water is disappeared. It was just a optical illusion. You felt that there is water, but it is not there. This is known as mirage. Same thing happens in the desert also. The desert, the Saudi Arabian guy, if he is seeing some camel from far away, he finds that the camel is fell in the water. That is because of mirage. But when he goes nearby, he finds the camel safe. So what happens here is a wave will pass from that object and that it will fall on the ground. Because light will travel faster in the hot air, which is near the ground. Near the ground you have hot air, right? So that light, it will bend up. It will hit the ground, it will bend up. There you can see the bigger wavefronts. If you draw that optical ray, you will find the inverted image, and also you can see some illusion that there is some water. Okay, so this is known as mirage. Now, as I told you, the two important conditions for which the total internal reflection occurs, these two important conditions, they are for mirage to occur also, because it is an application of a total internal reflection, or it is a phenomenon which is based on total internal reflection. Now let us talk about optical fibers. Optical fibers are another important application of total internal reflection. First of all, what is an optical fiber? It is a synthetic material. It is used for the propagation of light signals in desired direction. Desired direction means whatever direction you want, you can have that propagation of light signals in that direction only. So these optical fibers, they help you in doing so. Now what are optical fibers? As I told you, they are synthetic material, and it consists of thousands of very long fibers of fine quality, glass or quartz. Means these fibers are made of glass or quartz. These fibers are known as strands. One strand may have diameter of nearly 1 micrometer. Micro means 10 to the power minus 6 meter. And in light through multiple total internal reflections is propagated along this strand, in which index of refraction of core is greater than that of surrounding. Means there is something called as, you can say, like we say refractive index, no? That refractive index of core of this fiber, it is greater than that of surroundings. We call it as cladding. Here we have drawn this simple figure for this single strand of optical fiber. Here you can see how this total internal refraction is happening. You can see that the refractive index, it should be greater. For mu1, it should be greater than mu2. Mu2 is the refractive index of the surrounding. Mu1 is the refractive index of the optical fiber itself. Now for this also we need critical angle, right? Because it is also total internal reflection. There it was 1 upon mu, right? For a total internal reflection. Here, because we are bothered of two refractive indexes, that's why the critical angle sin IC will be equal to mu2 upon mu1. Mu2 is refractive index of the surrounding. Mu1 is refractive index of the fiber itself. Okay, the material of the fiber, the material with which the fiber is made. The refractive index is mu1. Okay. This is an example. You must have seen these lamps, the light lamps, no? Before, I think some 10-15 years, when optical fibers were invented, no? So every house had this decorative piece, the lamp. These are only optical fibers. Now what are the applications of these optical fibers? Because of the speciality of these optical fibers, what is the speciality? One is that there is no loss of light, right? I told you in total internal reflection, there is no loss of light. And other quality is that they will have this light propagation in particular direction, in any direction which you want, you can have it, isn't it? So the optical fibers have a lot of applications. For example, they are used in medical investigations of inner parts of the body or in surgical operations. Then they can reach the remote areas in human body in the form of catheter. This makes robot arm in surgery. See, actually, they say no, nowadays robots also do surgery. People say no. How they do is they use these optical fibers. Then in telecommunication, for transmission of data, sound or light or electronic signals over a long distance without any distortion, optical fibers are used. Then in photometric sensors, for measuring blood flow in the heart, all these, no, in medical purposes, optical fibers are used. Then in refractometers, for determination of refractive indices of liquids also, these optical fibers are used. One more very important application in medical field is that people do endoscopy. Doctors do endoscopy using these optical fibers. Endoscopy means they put some camera through your throat to see what is the infection in the lungs, right? That is known as endoscopy. In endoscopy also optical fibers are used nowadays. Now let us see few multiple choice questions based on this topic. First question is, just after the sunrise, the sky appears reddish because the blue and violet colors are scattered by a greater amount than the red color. The Whipguard thing, you know it, right? Next question. This question was actually asked in HSTR 2015 question paper. The question is, the optical fibers work under the principle of, yes, it is total internal reflection. Next question. For a total internal reflection, which of the following is correct? Light travels from rarer to denser medium, from denser to rarer medium. Light travels in air only, light travels in water only. It should travel from denser to rarer medium. Remember, this is the condition for total internal reflection. Next question. A ray of light traveling in a transparent medium of refractive index mu falls on a surface separating the medium from air at an angle of incidence of 45 degree. For which of the following value of refractive index the ray can undergo total internal reflection? See, we know that the critical angle is inversely proportional to the refractive index, right? Here refractive index, usually we denote it by mu, but here it is denoted by alpha. Just substitute the value. See, when sin I is greater than 1 upon alpha, or this refractive index is greater than 1 upon sin I. What is the angle of incidence? It is 45 degree, right? Sin 45. Actually, sin 45 is 1 by square root of 2. Then refractive index will become 1 upon root 2. So it will be square root of 2. It is 1.41. For which of the following value of refractive index the ray can undergo total internal reflection? Means it should be more than 1.41. Here in these options, there is only one option C which is more than 1.41. It is 1.5. Why it should be more? Why we told this? Because in total internal reflection, the angle of incidence should be greater than critical angle. That's why option C is the right answer. Next question. The critical angle for diamond is, they have given the refractive index. You can easily find the critical angle, right? Sin I is 1 upon 2, that is refractive index is 2, or I will be sin inverse of 1 upon 2, it will be 30 degree. These are little tough questions. I don't think they will ask in HSTR, but you never know, maybe in KREIS they will ask this type of questions. So it's better we have a look at this type of questions also. So B, 30 degree will be the right answer. Next question. The refractive index of a medium with respect to air for the critical angle 60 degree is given by. Of course, we have this formula, just substitute. Now we know that sin 60 is square root of 3. So 2 upon root 3. You just write the values. Root 3 will be 1.73. No, 2 upon 1.73 you do. You will get one answer. That will be option B. Next question. Optical fiber works on the phenomenon of. Yes, it is total internal reflection. The critical angle theta c in an optical fiber is given by dash, where n1 is the refractive index of the medium 1 and n2 is the refractive index of medium 2. We told it, right? It should be sin inverse n2 upon n1. Here refractive index is denoted by n. There we denoted it by nu. Next question. Optic fibers are used in. Yes, it is used in endoscopy. I told you there, right? Next question. Which material is used to prepare optical fiber as a transmission media? I told this point also when I started with optical fiber. It is glass and plastic. Next question. In optical fiber communications, the signal source is dash waves. It should be light. We don't need any other source, right? We need the light source only for optical fiber because it is total internal reflection. Dash is a guided medium. Guided medium. Guided medium means you can guide that, isn't it? That is fiber optic cable. Now let's talk about optical instruments. In optical instruments, we are going to talk about microscopes and telescopes. They have given binoculars in the syllabus, but I don't think they will ask because no one will ask anything about binoculars. I have not seen it anywhere till now. That's why we will focus on microscopes and telescopes. Now, what is a microscope? It is an optical instrument. It is used to visualize minute objects. We know it, right? Now, these microscopes, they are classified as simple microscopes and compound microscopes. This we should know. Simple microscope means the microscopes which we used in our laboratories in our class 11 and class 12. So these are simple microscopes which we used to use in our laboratories. Compound microscopes are very big microscopes which are used for research purpose. Probably you must have not seen them, but they are very big. Okay, so much I can say. Now in a simple microscope, you will have one convex lens of short focal length. It will be held close to the eye. If it is held close to the eye, then only you obtain the magnified virtual and erect image of that minute or small object. Okay, so this is called simple microscope or a magnifying glass also you can say. Now what is the magnifying power of this simple microscope? It will be 1 plus capital D upon F. F will be the focal length of that convex lens, where capital D is the least distance of distinct vision. Okay. When final image is formed at infinity, then you will have this magnifying power is equal to capital D upon F. Okay. Now, what are the applications of simple microscope? Jewelers and watchmakers, they make use of simple microscope as magnifying glass, and it is also used in science laboratories and it is used in reading maps. Now, let's talk about compound microscope. Compound microscope, it is used to see extremely small or very minute objects clearly. So, this I told you, right? It is used in research. In your research laboratories, compound microscopes are used or not. And this microscope, it consists of two converging lenses. One converging lens is called objective and the other one is the eyepiece. Here the conditions on base of which the compound microscope is built is that focal length of eyepiece will be greater than focal length of the objective lens, and diameter of the eyepiece also will be greater than diameter of the objective lens. Okay. And the magnifying power of compound microscope is equal to V0 upon U0 into D by FE, where U and U0 it is the image and object distance and all that you know it, right? And F is the focal length. D, as I told you, it is the least distance of distinct vision. Here, if the length of the tube in the compound microscope is equal to V0 plus FE, then when the final image is formed at this least distance of distinct vision, this magnification, it will become V0 upon U0 into 1 plus D upon FE. The first one, which is the V0 upon U0 into D upon FE, this was the magnification when final image is formed at infinity. Means it is a normal adjustment, you can say. In the normal adjustment, for the compound microscope, this was the value for magnifying power. But if the image is formed at D, that means at least distinct of distinct vision, then M will be equal to V0 upon U0 into 1 plus D upon FE. Okay, these two things you have to remember. See, they will not ask numericals based on this formula. Just you should have a gist. You should have a rough idea about these formulae. That is more than enough, I think. Now let us talk about the astronomical telescope. An astronomical telescope is an optical instrument. Is an optical instrument which is used for viewing distant objects situated in space. That objects in space, you can see them clearly and their magnified image using this telescope. The image of a distant object formed by this substance large visual angle. You should have big angles, then only you can see. There are two types of astronomical telescope. One is the refracting type astronomical telescope. The other one is the reflecting type astronomical telescope. The magnifying power for both these telescopes is F0 by Fe. But here again, when the final image is formed at infinity in a refracting type, you will have M is equals to F0 upon Fe. Again, if you see the length of the tube, which is equal to F0 plus Fe, M will become F0 by Fe into 1 plus Fe by capital D. Okay, this you should know. See, this is, I don't think they will ask anything about this, but just I am giving you one gist. Okay, again in reflecting type, no, you will have again F0 upon Fe only, but that F0, that is the focal length of the objective lens, will be equal to R upon 2. R is the radius of curvature. Okay, these are the two types of astronomical telescopes. Now there is one more point which you should know, that is the resolving power. For microscope also it is there and for telescope also it is there. For microscope, see, not only for microscope, for telescope also we have certain formulas for that. First of all, let's see what is resolving power of a microscope. It is defined as the reciprocal of the distance between two objects, which can be just resolved when seen through the microscope. Means two objects should be just, it could be differentiated through the microscope. That is known as resolving power. Now this resolving power equals to 2 mu sin theta upon lambda. That means the resolving power here for microscope depends on wavelength. Mu, that is the refractive index of medium between object and objective, and theta, that is the half angle of the cone of light from one of the objects, theta. Okay. For a telescope, it is defined as reciprocal of smallest angular separation between two distant objects whose images are seen separately. Here 1 upon d theta means resolving power is equal to A upon 1.22 lambda. Here also it depends on wavelength, but other thing is the diameter of the objective. Just you have to remember this formula and definitions will do. I will not go into much deeper here. Now let's see a few questions. Light of wavelength 4000 angstrom is incident at small angle on a prism of apex angle 4 degree. The prism has a mu v is equal to 1.5 and mu r is equal to 1.48. The angle of dispersion produced by the prism in this light is. See, don't see any options for this question because they are telling that light of wavelength 4000 angstrom means one wavelength is there. And they are asking angle of dispersion. Can dispersion happen for one wavelength? It is not possible, right? So none of these will be the option because dispersion will not occur for a light of single wavelength. Next question. Color of the sky is blue due to, yes, of course it is due to scattering of light. Next question. An astronaut in a spaceship sees the outer space as, it will be black. No scattering, no color. Okay, no scattering, therefore no color, therefore it will be black. Just after the sunrise, the sky appears reddish because, it should appear reddish because blue and violet colors are scattered by a greater amount than red color. Next question. An astronomical telescope has a large aperture too. It should have large aperture because it should have high resolution. Large aperture will give you high resolution. Next question. To increase the angular magnification of a simple microscope, one should increase the power of the lens. Because see, for the first question, no, the aperture of the objective lens of astronomical telescope, it is large to get better resolution. Because that resolving power, it is inversely proportional to wavelength and directly proportional to the diameter, right? Means that's why good resolution means large aperture, means large diameter. And here now one should increase the power of a lens. That is, the decrease of focal length of a lens is needed. Next question. The focal length of the objective of a telescope is 60 cm. To obtain a magnification of 20, the focal length of the eyepiece should be. We know that the magnification is equal to f0 upon fe, right? Means focal length of objective lens at the focal length of eyepiece lens. Substitute the values, you will get the right option. Option B should be the right answer, 3 cm. Okay. Now these two questions I am giving you as an assignment. Please pause the video here, read out the questions and give the answers in the comment section. I'll be happy to see your answers. Okay. That's it. I really hope that I helped you with this third part of the optics lecture. Please let me know your feedback, whether you feel there is some problem with my teaching or whatever is your problem. Please do let me know in the comment section. Also, you can join the Telegram channel. I will give you the link in the description. And also, as usual, please do share my videos, like them, and also subscribe to my channel if you have not subscribed still. Okay. Thank you. All the best. Bye.